Welcome back to the course on two-phase flow with phase change in conventional and miniature channels. Today, we will discuss the modeling of two-phase flow and in particular the homogeneous model. Modeling of two-phase flow is important to calculate pressure drop in two-phase flow and to design two-phase flow equipment. There are different types of models of two-phase flow. There are flow regime based models. These are for specific types of flow regimes. If we know the flow regime, then we can use the model for that particular flow regime. For example, there are models for annular flow, there are models for slug flow, and similarly there are specific models of different types of flow regimes. But suppose we do not know the flow regime, then there are some models which can be used regardless of flow regimes. The simplest of them is the homogeneous equilibrium mixture model, or in short it is called HEM model or popularly known as homogeneous model. In this, the two phases are assumed to be a homogeneous mixture, and the properties of the mixture are calculated by weighted averaging of the properties of the two phases. It is assumed that the velocities of the two phases are the same. Actually, the phase velocities are usually different, but for simplicity in this model, it is assumed that both phases are moving together with the same velocity. And it is also assumed that there is thermal equilibrium between the phases. That means, both phases are at the same temperature. If both phases are liquid and gas phases of the same substance, for example, water and steam, then both of them will be at the saturation temperature at the local pressure. So, therefore, the properties of the liquid and gas phases can be calculated by knowing the pressure. Then there is a separated flow model, which is comparatively general. In this, the separate motion of the two phases is considered, and the balance equations for the two phases are written separately and solved. The phase velocities are taken as different, but thermal equilibrium is assumed. Okay. Then there is a drift flux model. In this, there is a concept of drift flux which we will discuss later, and using that the relative motion between the phases is accounted for. But this combines the simplicity of the homogeneous model, but also takes into account the relative motion of the phases. The homogeneous model is used, but there are empirical correlations for the effect of relative motion between the phases. So, first we will discuss the homogeneous model. So, as I have already stated, in the homogeneous model, the two fluid is assumed to be a homogeneous mixture of the two phases, and the velocities of the two phases are assumed to be the same. Thermal equilibrium is assumed, that means the same temperature, and the properties are calculated by weighted averaging, and there is a two-phase friction factor which is used to calculate the frictional pressure gradient. So, suppose a two-phase mixture is flowing through a channel. Okay. And suppose the channel is at an angle theta with the horizontal. The inlet mass flow rate is m dot, and we will consider steady state. So, inlet and outlet mass flow rates are the same. The inlet pressure is P and the outlet pressure is P plus dP. We are considering a small element, infinitesimal element of the length dz. The axial coordinate is denoted by z. Okay. So, the inlet pressure is P, outlet pressure is P plus dP. The inlet velocity is u, outlet velocity is u plus du. As I have already mentioned, the velocities of both phases are assumed to be the same. The cross sectional area is A, that is this, and the wetted perimeter is denoted by Pw. The wall shear stress is tau w. So, Ug and Uf both are assumed to be the same and denoted by U. The weighted average properties are as follows. The V bar denotes the specific volume of the mixture, and V bar is equal to Vf plus x Vfg, and rho bar is the density of the mixture, which is the reciprocal of V bar. The mass flow rate m dot is equal to rho u a, and the mass flux, which is mass flow rate per unit area, will be equal to rho bar u and also equal to u upon V bar. Now, the mass balance. The total mass flow rate will be equal to the sum of the gas mass flow rate and the liquid mass flow rate. The gas mass flow rate will be total mass flow rate into quality m dot x or equal to G A x. The liquid mass flow rate will be m dot into 1 minus x equal to G A 1 minus x. Now, the momentum balance. The force due to pressure at the inlet is P A, and the force due to pressure at the outlet is P plus dP A. The force due to friction is wall shear stress into the area of contact, which is P w dz, and the weight is density into g sin theta into the volume of the element, which is A dz. Then the momentum flux at the outlet is mass flow rate G A into the velocity u plus du minus the momentum flux at the inlet, which is G A u. So, P A and P A get cancelled on the left hand side. So, we get minus A d P, and on the right hand side G A u gets cancelled. So, we are left with G A d u. Now, we divide all the terms by A dz, which is the volume of the element. So, we get dP by dz, and we take all the other terms to the right hand side. So, the first term is tau w P w by A, then G du by dz, and then rho bar g sin theta. So, on the right hand side, we can identify the three terms as follows. The first term is the pressure gradient due to friction, and it is equal to tau w P w upon A. Tau w is equal to f u square upon 2 rho bar, and if we consider a circular channel, then the perimeter is pi d and the area is pi d square upon 4, and then we simplify, and finally, we get 2 f by d into g square V bar. The second term is the pressure gradient due to acceleration, and it is equal to G du by dz, but u is equal to G V bar. So, we substitute, and then G can be taken out of the derivative. So, we get G square dV bar by dz, and V bar is equal to Vf plus x Vfg. Now, for simplicity, we will assume that the specific volume of the liquid phase does not change. Actually, it will change, but the change will be very small, so it can be neglected. That is, the compressibility of liquid phase is neglected. So, we need to differentiate only the second term, which is x VFG. So, we get this, and then we differentiate, and we get VFG dx by dz plus x dVFG by dz. Okay. So, here we have assumed Vf is approximately constant. Okay. Now, here we have VFG, this VFG is equal to Vg minus Vf, but Vf we are treating as constant. So, therefore, dVFG by dz is approximately equal to dVg by dz. Okay. So, we get this expression Vfg dx by dz plus x dVg by dz. So, dP by dz due to acceleration is equal to g square Vfg dx by dz plus x. Now, dVg by dz we rewrite using chain rule as dVg by dP into dP by dz. dVg by dP is a property. It is a derivative of one property with respect to another property. So, it is property of the material, and dP by dz is the pressure gradient, which is usually unknown, and we are trying to find it out. Now, the last term is the pressure gradient due to gravity. It is equal to rho bar g sin theta or rho g sin theta upon v bar. Okay. So, we get this dP by dz is equal to the frictional pressure gradient plus acceleration pressure gradient plus gravitational pressure gradient, and frictional is 2 f by d g square v bar, acceleration pressure gradient is g square Vfg dx by dz plus x dVg by dP dP by dz, and this is the unknown which is contained here, and plus g sin theta upon v bar. So, since dP by dz is unknown, we take it to the left hand side and combine it with the dP by dz on the left hand side. So, we get dP by dz into this 1 plus g square x dVg by dP, and on the right hand side we have 2 f by d g square v bar plus g square Vfg dx by dz plus g sin theta upon v bar. So, dP by dz, the pressure gradient, is equal to 2 f by d g square v bar plus g square Vfg dx by dz plus g sin theta upon v bar upon 1 plus g square x dVg by dP. Okay. Now, this term g square x dVg by dP, it represents the compressibility of the gas phase, and we denote it as minus m square. Okay. dVg by dP will be negative, because as pressure increases, the specific volume of the gas phase will decrease. So, now dP by dz becomes 1 upon 1 minus m square into these terms. Okay. So, m square we have defined as minus g square x dVg by dP, which is equal to g square x into absolute value of dVg by dP. Under certain conditions, we can simplify the expression for the pressure gradient. If the compressibility of the gas phase is negligible, which means m square is much less than 1, then m square can be neglected compared to 1, and 1 minus m square can be taken as approximately equal to 1. So, the denominator becomes 1 and we are left with only the numerator, and dP by dz in such case is equal to 2f by d g square v bar plus g square v f g dx by dz plus g sin theta upon v bar. And the first term can be identified as the pressure gradient due to friction, and the second term g square v f g dx by dz is the pressure gradient due to acceleration, and the third term g sin theta upon v bar is the pressure gradient due to gravity. Okay. Here everywhere with dP by dz we have put a minus sign, because usually the pressure gradient is negative. As you go downstream, the pressure decreases. So, the minus dP by dz will be usually positive. The pressure gradient due to friction is always negative, because friction always opposes motion. The pressure gradient due to acceleration can be positive or negative. Pressure gradient due to gravity can be positive or negative. Okay. Now, consider the limiting case when m square tends to unity. So, then 1 minus m square tends to 0. So, the denominator tends to 0 and the pressure gradient tends to infinity. What does this mean? It means that if you go on increasing the inlet pressure or go on reducing the outlet pressure, then the pressure drop will increase, pressure gradient can increase indefinitely, but the mass flow rate or the mass flux will not increase beyond a certain value. This is called choked flow. You must be familiar with choking in compressible flow, compressible gas flow. So, something similar to that happens in two-phase flow also. There is some maximum flow rate that can go through a given channel, and you cannot make more than that flow through the channel. What is that maximum flow rate? So, for that we set m square is equal to 1, and that gives g max square x dVg by dP equal to 1, and g max is equal to x dVg by dP whole raised to minus half, and the maximum mass flow rate is equal to. So, this is the maximum mass flow rate that can flow through the channel. Now, we will consider some numerical examples, but before that we will discuss how to calculate properties of fluids. So, there are property tables available for various fluids. Here we will consider the properties of steam water mixture. So, properties of steam water mixture can be obtained from steam tables, and there are equations of state. For water and steam, there is an international association for properties of water and steam, and its website is this. The equations of state can be downloaded from here, and there is software also. There is a steam tab companion, which is a free software, and it is based on IAPWS equations of state, which are very accurate. Let us look at that. The interface of the steamtab.exe looks like this, and if you want to calculate the properties of saturated water or steam, then you give input either temperature or pressure. So, let us give pressure in bar, 1 bar, and press the calculate button. So, here it gives the saturation temperature as 99.6 degrees C, and various properties are given. Similarly, if you select liquid, then it will give properties of saturated liquid at that pressure. If we select two phase and give a quality, let us say 0.1, 10% quality, and click the calculate button, then it gives the properties of the mixture. Then superheated and subcooled properties can also be calculated. So, suppose we want subcooled liquid water at 1 bar pressure and 25 degrees C. So, here it is giving the condition as subcooled, and it is giving the properties of the subcooled water at 1 bar and 25 degrees C. Now, suppose we want to calculate the properties of superheated steam at 1 bar and 125 degrees C. Now, it says that it is superheated and gives the properties of superheated steam. Okay. So, let us consider some numerical examples now. In the first example, we have water steam mixture at 100 kilopascal pressure, which is 1 bar, and it is horizontal flow through a pipe of diameter 2 millimeter. It is a small pipe and the length is 10 centimeter. Mass flux is 100 kg per meter square second. The inlet quality is 0, that means inlet is saturated liquid, and the heat flux is 20 kilowatt per meter square. We have to find the pressure gradient at 5 centimeter from the inlet, which is the midpoint of the pipe. So, we evaluate properties of water and steam at 100 kilopascal. The mu f, mu g and HFG, we have Vf, Vg and Vfg. Now, we will do a simple energy balance, and from that we can calculate the rate of change of quality with distance. So, dx by dz is equal to 4 q double prime upon g d HFG, and which is equal to 0.443 per meter. Here we have uniform heat flux, therefore, we are getting a constant value of dx by dz, and therefore, the variation of quality with distance will be linear, and at 5 centimeter at the midpoint, the quality will be half of the outlet quality, which is 0.0221. Now, dVg by dP, first we will calculate m square and check whether it is much smaller than 1 or not small. So, for that we have to first calculate dVg by dP. This we will do by numerical differentiation as delta Vg upon delta P. So, we take two values of pressure which are slightly different and find the Vg for these two pressures and take the difference. So, 1000 Pascal pressure difference has been taken, that means 100 Pascal and 101 kilopascal, 100 kilopascal and 101 kilopascal. At these two pressures, the value of Vg has been taken, and then we get the value of dVg by dP as minus 1.57 into 10 raised to minus 5 SI units. Now, using this we calculate the value of m square, which is 3.47 into 10 raised to minus 3. So, this is very small compared to unity, and if we neglect it, the error will be less than 1%. So, therefore, we can neglect it and assume that 1 minus m square is nearly equal to 1. So, 1 upon 1 minus m square is also nearly equal to 1. So, therefore, the denominator in the expression becomes unity and we need to consider only the numerator. Now, to calculate the frictional pressure gradient, we first calculate the Reynolds number, assuming that all the fluid is in liquid phase. So, ReFO is equal to GD upon mu F, and that is equal to 707. And therefore, the flow is laminar, and then we can use the friction factor relation for laminar flow, which is 16 by Re, and we get this friction factor 0.0226. The mixture specific volume V bar is equal to Vf plus XVFG, and that we get as 0.0180 meter cube per kg. First, for simplicity, we assume FTP to be approximately equal to FFO, which is equal to 0.0226, and then later on we will estimate FTP and do the calculations once again and compare. So, using this value of friction factor, we get dP by dz due to friction equal to 2 FTP by d g square V bar, which is equal to 4.07 kilopascal per meter, and the pressure gradient due to acceleration is equal to g square Vfg dx by dz, and this is equal to 7.50 kilopascal per meter. The pressure gradient due to gravity will be 0 because it is horizontal flow. So, we add all these and then get the total pressure gradient as 11.57 kilopascal per meter. Now, let us check for choking also. So, we calculate the maximum mass flux, which is x dVg by dP whole raised to minus half, and we get it as 1984 kg per meter square second, and the actual mass flux is only 100 kg per meter square per second, which is much below this value. Now, we will do a more accurate calculation. So, for that we have to estimate the mixture viscosity. So, we use Macadam's relation, 1 by mu bar is equal to x by mu g plus 1 minus x by mu f. So, mu bar is equal to 190.1 into 10 raised to minus 6 Pascal second. Using this, we calculate the two phase Reynolds number, which is G d by mu bar, and we get it as 1052, and the flow is again laminar. So, we calculate friction factor using laminar flow relation 16 by Re, and we get this friction factor, which is less than the friction factor calculated based on ReFO. So, the frictional pressure gradient is calculated as 2.74 kilopascal per meter. Acceleration pressure gradient is the same as before, and the gravitational pressure gradient is 0. So, we add all these three and get 10.24 kilopascal per meter. The previous calculation was 11.57 kilopascal per meter, and now we have got 10.24 kilopascal per meter, which is slightly different. Okay. Let us consider one more example of a larger channel. So, again it is water steam mixture at 100 kilopascal pressure, and this time it is vertical upward flow, and diameter is equal to 2 centimeter, length is equal to 2 meter. The mass flux is 1000 kg per meter square second. The inlet quality is 0, and instead of heat flux, here the outlet quality has been specified, which is 2%. We have to find the pressure gradient at z equal to 1 meter, which is the midpoint of the channel. The properties of water and steam at 100 kilopascal pressure are the same as before, and x at 1 meter will be half of the outlet quality, which is 1%, and dx by dz we get as total change in quality upon total length, which is equal to 0.01 per meter. Now, we calculate dVg by dP, which is the same as before. It is minus 1.57 into 10 raised to minus 5 SI units, and m square is equal to g square x dVg by dP, and this is equal to 0.157. So, now it is not negligible compared to unity, and we have to take it into account. The compressibility of the gas phase has to be taken into account. So, 1 minus m square is equal to 0.843, and 1 upon 1 minus m square is equal to 1.186. So, all the terms in the numerator have to be multiplied by this factor. Now, we calculate the Reynolds number, assuming that all the fluid is in the liquid phase, and it is equal to 7.07 into 10 raised to 4. So, it is turbulent flow. So, now we use the Blasius equation for turbulent flow through smooth pipe, 0.079 ReF4 raised to minus 0.25, and we get the friction factor as 4.85 into 10 raised to minus 3. The mixture specific volume is equal to 0.0180 meter cube per kg, and for simplicity first we assume FTP is approximately equal to FFO, which is this 4.84 into 10 raised to minus 3, and using this friction factor we calculate the pressure gradient due to friction, and here m square is also taken into account, and we get 10.36 kilopascal per meter. The acceleration pressure gradient is calculated as 20.1 kilopascal per meter. The gravitational pressure gradient is calculated at 0.646 kilopascal per meter, and we add all these three pressure gradients and get 31.1 kilopascal per meter as the total pressure gradient. Let us check for choking. The maximum mass flux is calculated as 2949 kg per meter square second. The actual mass flux is 1000 kg per meter square second, which is less than this value. So, no choking will occur. Now, for a more accurate calculation, let us use McAdams relation and calculate the mixture viscosity, which is 232 into 10 raised to minus 6 Pascal second, and using this we get the Reynolds number for the two phase mixture as 8.62 into 10 raised to 4, and again it is turbulent flow. So, using the Blasius relation we get the friction factor as 4.61 into 10 raised to minus 3. Now, using this friction factor we get frictional pressure gradient as 9.85 kilopascal per meter. The acceleration pressure gradient is the same as before, gravitational pressure gradient is also the same as before, and by adding all of these we get 30.6 kilopascal per meter. Compare this with the previous value, which is 31.1 kilopascal per meter. So, there is slight difference if we consider the viscosity of the mixture, but not much difference is there. Another thing to be noticed is that in this example, the frictional pressure gradient and the acceleration pressure gradient are large compared to the gravitational pressure gradient, which is small, and the acceleration pressure gradient is larger than the frictional pressure gradient. But these will change from problem to problem, and sometimes one term may be dominant, sometimes another term may be dominant. In the previous example, we had gravitational pressure gradient was 0 and acceleration pressure gradient there also was larger than the frictional pressure gradient. But this is not always true. Let us see in the next example what we get. So, let us take one more example. This time we take a high pressure 10 megapascal and it is vertical channel, diameter is 2 centimeter, length is 2 meter. Mass flux is the same as that in the previous example, 1000 kg per meter square second. Inlet and outlet qualities are also the same, 0 and 2%. Properties of water and steam at 10 megapascal are evaluated as follows. Mu f is 81.80 into 10 raised to minus 6 Pascal second, mu g is 20.27 into 10 raised to minus 6 Pascal second, V f is equal to 1.453 into 10 raised to minus 3 Pascal meter cube per kg, V g is equal to 1.803 into 10 raised to minus 2 meter cube per kg. So, V g in the previous cases was much larger than V f, but here it is not so large. V f g is 0.01658 meter cube per kg. The quality at the midpoint will be 1% and dx by dz is equal to 0.01 per meter. Now, we calculate dVg by dP by considering two slightly different pressures. We calculate the pressure is 10 megapascal, which is 10,000 kilopascal or 100 bar. So, we take 100 bar and 101 bar and find out Vg at these two pressures and then take the difference. So, we get dVg by dP equal to minus 2.20 into 10 raised to minus 9 SI units, and g square x dVg by dP, which is m square, is obtained as 2.20 into 10 raised to minus 5, and this is very much less than 1. So, we can safely neglect it and we can take 1 minus m square equal to 1 and 1 minus m square raised to minus 1 also equal to 1. Now, REFO is calculated as 2.44 into 10 raised to 5. So, it is turbulent flow, and using the Blasius relation we get FFO equal to 3.55 into 10 raised to minus 3. The mixture specific volume is 1.649 into 10 raised to minus 3 meter cube per kg. FTP we assume to be equal to FFO, and then using this we calculate the frictional pressure gradient, which is 0.575 kilopascal per meter. The acceleration pressure gradient is 0.166 kilopascal per meter. Gravitational pressure gradient is 6.05 kilopascal per meter. So, in this case the gravitational pressure gradient is dominant and the frictional and acceleration pressure gradients are much smaller than gravitational pressure gradient, and between the frictional and acceleration pressure gradients the frictional pressure gradient this time is larger. So, why is it so? Because the pressure is high, so the density of the gas phase is also high compared to the lower pressure, and therefore, the weight of the fluid is more, and therefore, the gravitational pressure gradient is large. The acceleration pressure gradient depends on VFG, and VFG is the difference between the specific volumes Vg minus Vf, and at high pressures the difference is less, VFG is small, and therefore, we get less acceleration pressure gradient. Then the frictional pressure gradient, it is proportional to V bar, and V bar is also less compared to that at lower pressure. So, therefore, the frictional pressure gradient is also less. Now, we add all these three pressure gradients and get the total pressure gradient as 6.79 kilopascal per meter. Now, let us check for choking. So, G max is obtained as 2.13 into 10 raised to 5 kg per meter square second, and the actual mass flux is only 1000 kg per meter square second, which is much less than this value. Now, for a slightly accurate calculation, we estimate the mixture viscosity using McAdams relation is 79.4 into 10 raised to minus 6 SI units. The Reynolds number for the two phase mixture is 2.52 into 10 raised to 5. So, the flow is turbulent, and then we use the Blasius relation to calculate friction factor, which is 3.53 into 10 raised to minus 3. This is only slightly different from the previously calculated friction factor, and we calculate the friction pressure gradient, which is 0.572 kilopascal per meter. The previous one was 0.575 kilopascal per meter. So, there is very small difference. The acceleration pressure gradient will be the same as before, gravitational pressure gradient will be the same as before. So, the total pressure gradient is 6.79 kilopascal per meter, and previously we had also calculated 6.79 kilopascal per meter. So, up to 3 significant figures, there is no difference if we consider the mixture viscosity instead of the liquid viscosity. Okay.